We're going to review some equilibrium calculations, talking about equilibrium constants and doing some fundamental equilibrium calculations. The problems I'm going to do were either taken or modified from chemistry, a book by Riddell and Navidi, West Publishers, 1990. It was a book that I had on my bookshelf. Okay, so we're going to start with this reaction, phosphorus pentachloride, decomposing in equilibrium with phosphorus trichloride and chlorine gas. And this reaction was studied at 250 degrees Celsius. And so in this problem, we are starting with 1 molar phosphorus pentachloride in a 10-liter container. 1 mole of phosphorus pentachloride in a 10-liter container. Then we let it reach equilibrium, and at equilibrium we measure the amount of chlorine in the reaction and find there is 0.47 moles. Okay, and so we need to do this. The question is, first, what is the equilibrium concentration of all of the components of the reaction mixture? So we can start and set up an ice table. That is, we can look at this reaction, right? Phosphorus pentachloride, phosphorus trichloride, and chlorine. We can look at the initial concentration. We can look at the change in concentration, and we can then figure out what's at equilibrium. Now we have to remember we're in 10 liters, right? So we have 1 mole in 10 liters. So 1 mole divided by 10 liters is, 0.1 molar. And I think the problem was given with 3 significant figures. And so here we have 0.47 moles of chlorine in our 10 liters. And so at equilibrium, that means we have 0.047 molar. That's a bad 7. 0.047 molar chlorine. Okay? So if we started at 0 of those, which it didn't tell us that we put in anything but that. Now we know that what has to go in here is plus 0.047 molar. Right? It had to go up that much. Right? Since chlorine and phosphorus trichloride react 1 to 1, every time we make 1 mole of chlorine, we also make 1 mole of phosphorus trichloride. So that means phosphorus trichloride has to be plus 0.047 molar. And since every time we make a mole of chlorine, we have to use up 1 mole of phosphorus pentachloride. Phosphorus pentachloride is going to be minus 0.047 molar. Right? And so that means the other two at equilibrium are going to be 0.047 molar. And 9 minus 4 is 5, 0.053 molar. And so those are the equilibrium concentrations of all components in the reaction mixture. Now it wants us to figure out the equilibrium constant. Right, so the equilibrium constant expression is concentrations of products, so that's going to be phosphorus trichloride times chlorine, right? There's no, the coefficients here are 1, and so there's the implied 1 as the exponent here, divided by the reactants, phosphorus pentachloride. We put in those concentrations. And we do the math, and we come up with an equilibrium constant of 0.04168. And I'm keeping more, right? So to 3 significant figures, right? 2 to 3, it would be 0.04, given what I've given there, 2. But we will keep this in mind because we will do more calculations with it, and we don't want rounding to affect our further calculations. So you'll see that number again. Okay, so we've got that same system, phosphorus pentachloride decomposing into phosphorus trichloride and chlorine gas. We've determined the equilibrium constant at the temperature that we're working, and now we're given a new situation. We're going to start the reaction with 1 mole of each of the components in the 10-liter container. Our first question is, are we at equilibrium? And if not, which direction would we expect the reaction to move? And so for that, we use our reaction quotient Q, right? So Q is expressed in the same way that the equilibrium constant is. That is, it's the concentration of products, right? The product of the concentrations of products divided by the product of the concentrations of reactants, right? And then we put our concentrations in, and remember we've got 1 mole in 10 liters, so each one is going to be 0.1 molar. And so we end up, right, when we do our math, I like it when the math is easy. It doesn't happen for us very often, right? A 0.1 cancels a 0.1. And we end up, without even having to do any calculations, that our Q is 0.1, right? So in this case, our Q is greater than the equilibrium constant, right? So in order to move toward equilibrium, Q has to get smaller, right? Q has to go down. Well, in order to go down, if we look at this, that means we need a smaller numerator, products have to get smaller, and a bigger denominator. Reactants have to get bigger. So the fact that Q is too large tells us that overall our reaction is going to have to go to the left. And so we can set up our ice table knowing that our reaction is going to move to the left. And so we can set it up again, right? We've got our PCl5, our PCl3, our Cl2, right? Our phosphorus pentachloride, our phosphorus trichloride, and our chlorine, right? Initially, they're all at 0.1. These numbers probably have 3 significant figures, right? Our change is what we just determined, right? To go left, our phosphorus trichloride has to go up X. Our phosphorus, that's pentachloride. our phosphorus trichloride has to go down the same amount, and our chlorine has to go down that same amount. So when we reach equilibrium, we're going to have 0.1 plus x, 0.1 minus x, and 0.1 minus x. And that's where we will start our equilibrium calculation. This is where we ended on our previous slide, right? So we have expressed our equilibrium concentrations of each component. Let me just add that just to make it a little clearer. So this is, right, the bottom line of our ice table. And so now we can express our equilibrium constant, right? Our equilibrium constant was 0.04168, and that's going to be equal to our concentration of phosphorus trichloride, which is 0.1 minus x, our concentration of chlorine, which is 0.1 minus x, and our concentration of phosphorus pentachloride, which is 0.1 plus x, right? And then we can expand that, right? We can multiply both sides by this term, and we can multiply this term through. And when you do that, you end up with this 0.004168 plus 0.04168x equals 0.01 minus 0.2x plus x squared. And then when we gather our terms, we get 0 equals 0.005832 minus 0.24168x plus x squared. That fits the quadratic equation. So now we'll go to the quadratic. Okay, I've transferred over our equation that we need to solve by the quadratic. And so if we plug this into the quadratic, we get, see if I can get this on here just to walk us through the quadratic again. So x is equal to plus, right, the negative of b, so 0.24168 plus or minus the square root of negative 0.24168 squared minus 4. A is 1, C is 0.005832. All over 2 times A, that is 1, right? And so we can work this out, right? And so that's going to be equal to 0.24168 plus or minus. This is the square root. B squared is 0.058492 minus 0.023328 when I worked it out, all over 2, which is equal to 0.24168 plus or minus square root of 0.0350812 all over 2, which is equal to 0.24168 plus or minus 0.18730 all over 2, right? And so that is equal to, right, depending on the plus or minus, so x is equal to 0.42898 over 2, which is equal to 0.21449, or, change colors here, x is equal to 0.05438 over 2, which is equal to 0.02719. So those are our mathematically valid solutions for a quadratic. Now we have to figure out what's physically valid. Now we have to go back to the way that we defined our concentrations at equilibrium, right? And look and see which makes sense, right? It would make sense to add this to 0.1, right? Adding is not a problem. But if we look here, this number is bigger than our beginning number, so if we try to subtract this from 0.1, we're going to get a negative concentration in both terms. Negative concentrations don't make sense, right? So the negative concentration not making sense tells us, while it's a valid mathematical answer, it's not a valid physical answer. So let's look at our other choice, right? Our other choice is a smaller number. Adding it makes a number, but it is smaller than 0.1. So when we subtract this from 0.1, we would still get a positive number. A positive number is at least a reasonable concentration. So that argues that we should at least consider this and test it to see if it is an appropriate answer, right? And so now we have to use, we can't get satisfied with just getting the mathematical answer. We have to go back to the way we defined our problem before we get the final answer. So we've said that our concentration of phosphorus pentachloride is 0.1 plus X, which is 0.02719, right? And that's going to be equal to 0.12719, and probably to 3 significant figures, we would report that as 0.127 molar. Our concentration of phosphorus trichloride is 0.1 minus our 0.02719, which is going to be equal to 0.07281, given our subtraction and that we're significant to the third place, probably to the proper number of significant figures that would be significant to the third decimal place. We would probably report that as 0.073 after subtracting molar. And the same thing would be true for chlorine. 0.1 minus 0.02719 equals 0.073 molar with the same consideration. If we take our original numbers, right, our unrounded numbers, that is, if we take this number, we take this number, and we take that same number unrounded here, if we put them back in our equilibrium constant expression, if we put them back in our equilibrium constant expression and calculate that out, we get 0.04168, which was our initial equilibrium constant. That gives us confidence that we've done our calculation correctly. Now we have a reaction where hydrogen gas is reacting with iodine gas to make 2 moles of hydrogen iodide gas. We know the equilibrium constant at this temperature is 50.3 when expressed in concentration terms. And so we are given concentrations. Since one of them is 0, we know we can't be at equilibrium, and we know then that the reaction, in order to reach equilibrium, we have to make some of that. So we already know in which direction our reaction has to go. It has to go in a way to make the 0 thing not 0 anymore. And so we can set up our ice table, right? And so we've got for hydrogen, for iodine, and for hydrogen iodide. We've got our initial concentrations, we've got the change, and we've got equilibrium. And so it tells us, right, already in molar, that this is 0.2. These were given to 3 significant figures in the original problem, so we'll assume 3 significant figures through the problem. This is 0.1. This is 0. Since we know we have to make some of this to reach equilibrium, since they react 1 to 1, we're going to use up 1 mole of that, and we're going to use up X moles of that, right? And so we would have 0.2 minus X and 0.1 minus X as our expression of the equilibrium concentrations of hydrogen and iodine. And so now we will put those into our equilibrium constant expression, right? And so our equilibrium constant expression for this would be that our Kc, right, 50.3 is going to equal the concentration of hydrogen iodide squared, right? Remember, right? Can't miss that coefficient, divided by the concentration of hydrogen and the concentration of iodine. And they are both, right, they're both have a coefficient of 1, so we have an implied coefficient of 1 there and there. And so we substitute in our definitions. So that is going to be, ooh, you guys about made me make an error, right? I almost missed right? We have to pay attention, right? Because this 2 is going to affect this stoichiometry. If x of these are used up, then that means we're going to have to make 2x of that, which means our final here is going to be 2x. And so that, right, we almost really messed up our problem, right? Got going too fast and didn't pay attention to that stoichiometry. So now when we fill in our equation, that's got to be 2x. And then it's all squared. 0.2 minus x and 0.1 minus x. That's the proper expression for that term. When we expand that out, you get an expression that looks like this. Let's see if I can do this. We get 1.006 minus 15.09 x plus 50.3 x squared equals 4x squared. And then when we gather our terms, right, let's make this, let's stay bright. When we gather our terms, we get 46.3 x squared minus 15.09x plus 1.006 equals 0. That is our quadratic that we will work through to find our solutions. There's our equation moved over into a new clean workspace. So if when we put that in the quadratic, we get a quadratic that looks like this. X equals a negative of negative 15.09 plus or minus the square root of negative 15.09 squared minus 4. A is 46.3. C is 1.006. Square root, all divided by 2 times 46.3, 2a. Right? So when we work that out, right, I will shorten this a bit, not go through the whole thing again, although I did on my paper, right? We get that x is equal to 15.09 plus or minus 6.434 over 92.6. So that means x can equal 21.524 over 92.6, which is 0.2324, or x can equal 8.6560 over 92.6, which would equal 0.005 0.0935. Those are the two mathematical solutions for our quadratic. Here's our information moved over, right? So here is how we defined our equilibrium concentrations of each component. Here are our two potential values of x we just found from our quadratic. And again, we have to look and see what makes sense physically. And so if we look, right, this point 2 is bigger than this point 2. If we subtract this from this, we will get a negative number. A negative concentration makes no sense. 0.1 minus this is going to give us even more negative number. So physically, that doesn't make sense because we can't have a negative concentration. If we look at this, right, 0.0935 is less than 0.1. Even there, we will get a positive number. And so at least at this point, it looks like this might be a reasonable answer. And now we have to go through and define our final concentrations, using our x as and using the way we defined them before, right? So our concentration of hydrogen at equilibrium we said was going to be 0.2 minus x, which would be 0.2 minus 0.0935, right? Which would equal 0.1065. And probably that 0.2 had 3 significant figures, so the best reporting would probably be 0.107 molar. Right? So the concentration of iodine we said was 0.1 minus x, so that's going to be 0.1 minus 0.0935. That's going to be equal to 0.0065. Given that this is a subtraction, and this actually ends up being 652 if you don't round early, but still we're probably only going to be significant in these 3 places, so the best reporting is going to be 0.007 molar if you're worried about significant figures. And our concentration of hydrogen iodide was 2x after we corrected ourselves earlier when we almost messed it up. So that's going to be 2 times our 0.0935, which is going to be 0.187 to 3 significant figures molar. If we put all of those numbers back in our equilibrium constant, we get the equilibrium constant, which was, into our equilibrium constant expression, we get 50.3 if we put the unrounded numbers in, so our numbers check out.